Hey guys, this is section 1.5. We're going to talk about inequalities. So, it's probably going to kind of be a long one because it's a really, really important topic. Now you know if you have an equation like x plus 3 equals 5, it has exactly one solution, x equals 2. That's it. It's the only solution to that equation. But as soon as you turn it into an inequality and you say x plus 3 is greater than 5, then you say x is greater than 2, and it now has infinitely many solutions. There are infinitely many answers that make this sentence true. For instance, any number greater than 2. Pick one. How about 10? If you put in 10 for x, 10 plus 3 is 13, which is greater than 5. Any number bigger than 2, when you plug it in for x, is going to make this inequality true. Let's review some of the symbols. This one is greater than, this one is less than, this one is less than or equal to, and this one is greater than or equal to. We talked in class a little bit about how less than looks like an L if you tip your head, or that it points to the left, and that's how you know it's less than. Simply memorizing that it eats the bigger number is not enough. You have to know the names of the symbols. You also have to know how to graph them on a number line. So for instance, x is greater than 2, we would put an open circle at 2 with an arrow to the right. Hopefully you remember that. If it was x is less than or equal to negative 1, you would put a closed circle at negative 1 with an arrow to the left. Now some teachers teach it to do it right on the line. What I find is when you do that it ends up looking all messy and gross, so I like to do it above the line with one line. What if you had to solve the inequality negative 3 times 2x minus 5 plus 1 is greater than or equal to 4. This is the same idea as solving an equation. You distribute the negative 3, so you get negative 6x plus 15 plus 1 is greater than or equal to 4. Now this plus 15 is a little confusing. It's negative 3 times negative 5, so that's a positive 15. So when we combine like terms here, we have negative 6x plus 16 is greater than or equal to 4. We're going to subtract 16 from both sides. We're going to go on to the next page. Negative 6x is greater than or equal to negative 12. Now this is where inequalities get a little tricky. And let me just do another example really quickly. Negative x is greater than or equal to 5. If I asked you to solve that inequality, most of you would say, oh, divide both sides by negative 1, x is greater than negative 5. And then I would ask you to pick a number that's greater than negative 5 and check it in the original problem. A number that's greater than negative 5 is 0. 0 is greater than negative 5. So, if this solution is correct to this problem, then it should work in the original when I pick 0. Negative 0 is just 0, which is not greater than or equal to 5. So the problem with inequalities comes in when you have a negative coefficient of x. The number in front of x is negative. If the number in front of x is negative in the very last step of the problem like this, when you divide by negative 1, you must also turn this symbol around in order to make it true. So now if we check it, what's a number that's less than or equal to negative 5? How about negative 10 is less than or equal to negative 5? Plug negative 10 in for x here. If I do negative 10, look what happens. Negative negative becomes positive 10 is greater than or equal to 5. So when I flip the sign around, it actually makes the original statement true, which is what we want. Math is not arbitrary. We want things to be true. So, in this situation, in the very last step before we divide, the number in front of x is negative. So therefore, when we divide by negative, we must flip the sign over. And negative divided by negative is positive 2. Now, if you remember, the original problem was negative 3 times 2x minus 5 plus 1 is greater than or equal to 4. Let's check our answer just for fun. I'm going to pick a number that's greater than or equal to 2, but I want to pick an easy number. So I'm going to pick 10, because I like 10. So we're going to let x be 10 for right now, just to try it out, to check. So then we're going to say negative 3 times 2 times 10 minus 5 plus 1 is greater than or equal to 4. 2 times 10 minus 5, 20 minus 5 is 15. Negative 3 times 15 is negative 45 plus 1 is not going to be greater than or equal to 4. This is going to be negative 44, so this is not true. So that's why this is not correct. Okay, x is greater than or equal to 2 is not correct because I didn't flip the sign. Now you probably all caught that when I wrote it, like, oh, you didn't flip the sign, you did it wrong. Well, there's proof why I did it wrong. If x was greater than or equal to 2, then 10 would make this sentence true. But when I divided by a negative, I should have flipped the sign around. So it should be less than or equal to 2. What's a number that's less than or equal to 2? Well, 0 is the easiest one to pick. 2 times 0 is 0. Minus 5 is negative 5. Negative 3 times negative 5 is positive 15. Plus 1 is 16, which is greater than 4. So this is the correct answer. If you forget to flip the sign, you will get it wrong. It's not correct. Hopefully by now you won't forget because we will have done it a whole bunch of times. Let's talk about some words for some inequalities. For instance, in a word problem, if you see something like at least, or what are some other words? Well, at most is the opposite. At least, think about it. If I say you're going to get paid at least $10 to do this, does that mean you could get paid less than $10? No, you'd have to get paid greater than or equal to $10. So if you see at least in a word problem, greater than or equal to is the symbol you're going to use. If I say you're going to get at most 5 hours of homework, at most, can you get any more than 5 hours? No, you're going to get less than or equal to 5 hours. So at least is greater than or equal to, at most is less than or equal to. If you're unsure, put it into something you know, like homework or money. Those are two things that are always good to use as examples with students because you guys always know about those. Okay, let's try a word problem. Here's a word problem. A movie rental company offers 2 subscription plans. You can pay $36 a month and rent as many movies as you want, or you can pay $15 a month and $1.50 to rent each movie. How many movies? So what don't we know? We don't know how many movies. So X is going to represent how many movies. And we're going to try to figure out how many movies must you rent in a month for the first plan to cost less than the second plan. So the first plan is $36 a month. So 36. And we want that to be less than, the second month is 15 plus $1.50 per movie. Let's solve this inequality. We're going to minus 15. And then we're going to divide by 1.5. And the answer comes out to be 14. Now this is confusing because you're used to having your variable on the left-hand side. But notice, if the inequality is eating the x when it's on the right-hand side, when you rewrite it on the left-hand side, it has to keep eating the x. You can't just switch the x and the 14 without switching the inequality. So if you want to rewrite it so that the variable's on the left, make sure that it's still, if it's eating it in the original, that it's still eating it in the answer. And then your answer would be, you must rent at least 14 movies for the first plan to cost less than the second plan. And yes, you should write all of that out because we are a school of literacy and we like to write. Now, what happens when you get one that comes out weird? Let's try this one. 4 times 2x minus 3 is less than 8 times x plus 1. 8x minus 12 is less than 8x plus 8. Subtract 8x from both sides and you end up with negative 12 is less than 8. Is negative 12 less than 8? It sure is. So this is always true. Always. No matter what number you pick for x, pick one. Let's pick 100. When I put 100 in there, 2 times 100 is 200, minus 3 is 197, times 4 is like 600 and something. 8 times 101 is 800 and something. It's actually 808, which is obviously bigger than whatever the 600 something was. So no matter what number you put in for x, let's try 0. 2 times 0 is 0, minus 3 is negative 3. 4 times negative 3 is negative 12. 0 to plus 1 is 1, times 8 is 8. This number will always be less, so always true. There are problems like that. Obviously, I just gave you one. There are also problems that come out to be sometimes true. That's usually what happens. Sometimes true is when you end up with an inequality like x is less than 5. If you end up with that, then that would be a sometimes true, because it's only true if x is less than 5. Then there's going to be some that are always true. Oh, I already did always true. There's going to be some that are never true. Let's try that. Negative 2 times 3x plus 1 is greater than negative 6x plus 7. Distribute, so negative 6x minus 2 is greater than negative 6x plus 7. When I add 6x to both sides, they cancel out. So I have negative 2 is greater than 7. Is negative 2 ever greater than 7? No. So your answer would be never true. Okay, let's get to some hard ones. These have all been pretty easy. There are some inequalities that say or say and. So for instance, here is an and inequality. 7 is less than 2x plus 1. And 3x is less than or equal to 18. Our answer has to be true for both of these inequalities. So first we're going to solve this one. We'll go minus 1. We'll divide by 2. So this says, if I read this, 3 is less than x, but we like to start at the variable. So if we read this starting at the variable, it would say x is greater than 3. And when I divide this one by 3 on both sides, x is less than or equal to 6. So we need to show on a number line that all the possible answers are between 3 and 6, but not equal to 3, possibly equal to 6. So when you have an and problem, the answer is always going to look something like this. It's going to be two things connecting. Make sure you don't do this, because what that says is all the answers this way and all the answers this way, which is essentially all real numbers, which that's not true. The answer has to be between 3 but not including 3, and less than 6 but possibly 6. So this is how an and inequality should look, with two endpoints connected in the middle. An or, and let's check that. I should have checked that. Pick a number between 3 and 6. How about 5? Which is clearly not halfway, but whatever. Put in 5 for x. 2 times 5 is 10, plus 1 is 11. Is 7 less than 11? Yes. 3 times 5 is 15. Is 15 less than or equal to 18? Yes. So a number in between 3 and 6 will make both inequalities true. An or inequality looks something like this. So to solve this inequality, you're going to go minus 7 from both sides. So k is greater than or equal to negative 1, or subtract 8 from both sides. k is less than negative 5. If you were to graph this on a number line, here's 0, here's negative 1, here's negative 5. K is greater than or equal to negative 1 looks like this. K is less than negative 5 looks like this. This is going to always be true for OR inequalities. They're going to go away from each other because either something over here makes it true or something over here makes it true. One more example. Sometimes an AND inequality looks like this. This actually says 5 is less than x plus 1 and x plus 1 is less than 13. You can solve these separately like this, or you can do it all in one shot. We're going to do it separately for now. So we're going to subtract 1 from both sides. So 4 is less than x, and subtract 1 from both sides over here, x is less than 12. So when you look at it on a number line, if you did it correctly, they should connect. So greater than 4 goes this way, less than 12 goes this way, and you have a nice little line segment with 2 endpoints on your number line. That's it! I think we're done. Say hi to Miss A. Hi, Miss A! Hi. We need a riddle to conclude our video just so that they watch the whole thing. Let's see. What happens once in a minute, twice in a moment, but never in 1,000 years? See ya!